That's right. Chiral Majorana fermions in condensed matter materials. So thanks for inviting me here. So I'm going to try to make a connection between the subject of this workshop and what I work on, which is condensed matter materials. So this work was done in collaboration with David Alspaugh, who is here in the back. There's David. So and also Mark Goerbig and Pascal Simon. And we have a preprint that just was submitted a few weeks ago, and it's submitted. It's under review right now. So what I want to talk about today is topological quantum computation. So that's the motivation for what we're going to discuss. And you might have heard a recent article in Wired magazine pointed out that topological quantum computing has long been a beautiful dream.
You've been stalking me.
Two top scientists are now facing off over whether it will exist by 2030. It's funny when I see that, I think it's more than 10 years in the future, but yeah, it's right around the corner. And so this is the two top scientists in question were John Preskill and John Dowling from LSU. And so I guess the bet is, so you claim that there's going to be no topological quantum computation within 10
There
years,
will
right?
be no demonstration of a 2-qubit gate
I see.
in any system
I see.
before March 1st, 2030.
Okay. So we'll see. So I'm definitely not going to present that. What I'm going to do is I'm going to discuss one possible.
We didn't even ask what the bet was for. It's a
Yeah.
pizza and a beer.
Oh yeah, it's a pizza and a beer. I saw that from the
That's the
article.
important
It's
part.
what kind of pizza or beer?
Yeah. New
Not
York,
defined.
New York pizza, Chicago pizza is lasagna.
So one way to achieve topological quantum computation that's been proposed is to use what are called Majorana fermions. So essentially, one way to think about it qualitatively is that a Majorana fermion is like half of an electron, and that sort of makes it immune to decoherence. The first possible use of these is through what's called a Majorana zero mode. So I'll discuss those in some detail. So the Hilbert space associated with these Majorana zero modes is very large, and theoretically it should be possible to braid these to implement quantum operations and solve this bet. Unfortunately, experiments have found this braiding to be exceptionally difficult, so it's very difficult to actually do this in practice, which has led people to pursue other options. So these other
And by
options
difficult, you mean impossible.
that's right.
No one has demonstrated this in any system
No.
whatsoever.
They've seen evidence of Majoranas, but not braiding. Yeah, it's definitely very difficult. So yeah, I should upgrade this difficult to impossible probably. But I mean, you never say that because it could be that the experiment will be done tomorrow.
Yeah,
You never know.
that's what the bet's all about.
That's what the bet's all about, exactly. So there's a new type of chiral Majorana, new type of Majorana fermion called a chiral Majorana that, in principle, is easier to braid. And so this was proposed by Shuqing Zhang and co-authors in 2018. And so I won't talk about this device in detail, but basically it's some kind of condensed matter interferometer device that can implement the same type of braiding operation that's shown in this cartoon here. So our work is sort of on the condensed matter side. We're interested in Majorana fermions, chiral Majorana fermions in topological superconductors. And what we find is that these Majoranas are accompanied by additional low energy states. So essentially, even these chiral Majorana modes, there's other low energy states. And one question is, how will these additional states impact quantum operations? So, and this is sort of our question for the future. So, okay, so I'm going to review Majorana fermions. The first thing I want to start with is conventional fermions. So what I mean is electrons, right? So the way we describe conventional fermions theoretically is through creation and annihilation operators that are similar to what you have in the quantum harmonic oscillator. So we have a creation operator that this creates a fermion in quantum state I, and we have an annihilation operator that annihilates a fermion in quantum state I. So these operators allow us to express any many bodies wave function in terms of acting with these operators on the vacuum state. So here's some wave function, and as an example, I've put two fermions in this state. So we have a product of creation operators acting on the vacuum. So this is just to set up the notation. So we know that identical fermions have a minus sign under exchange. And this minus sign is encoded in the algebra of these operators. Okay, so for example, you can essentially, one of the algebraic relationships is that psi dagger is a delta, a Kronecker delta function minus psi psi dagger psi. So this minus sign is exactly the minus sign for fermions. It's the Pauli exclusion principle. A related statement is that psi I dagger psi j dagger is minus psi j dagger psi I dagger. This is the Pauli exclusion principle because if I set I equal to j, I get it must vanish. So psi I dagger vanishes. So this is the Pauli principle. And what I'm trying to get across is that once we know this operator algebra, these rules, that sort of tells us how to, tells us everything we need to know about these fermions, or a lot of what we need to know about these fermions. So, so now what I want to do is describe Majorana fermions. So Majorana fermion is half of a fermion, half of a regular electron. So, okay, so how do we do that? Well, we're going to split the fermion creation and annihilation operator into real and imaginary parts. Okay, so even though they're operators, I can still sort of say, well, let's write this psi as 1/2 a different operator, gamma, plus I chi. So gamma and chi are new operators. They're real in some sense. And I can define psi dagger as, if I take the adjoint of this, I get gamma minus I chi. So this gamma and chi operators, these are Majorana operators. Okay, so if I invert these relationships, if you look at these, it sort of says that these are real, right? So if I take the adjoint of these, by construction, I get the same thing back. So these are charge neutral operators that can describe Majorana particles. And the question you might ask is this useful for anything? It turns out that there are systems that can exhibit these types of Majorana excitations. So, okay, but before I get to that, I want to describe the Majorana algebra. So we have the algebra for fermions on the previous slide, and so we can just derive the algebra for these Majorana operators. You just plug into the previous formulas. And so the second says that 2 of these is equal to 1. So gamma is 1, and gamma chi is minus chi gamma. So this is sort of the Pauli principle. Okay. So if we generalize this to many Majoranas, we get this is the Majorana algebra. Okay. So are there any systems where this splitting is useful? So the answer is, in principle, yes. But as we've been discussing, it's not clear how to actually observe the braiding that we discuss. So, but in some sense, the first realization I'll discuss are so-called Majorana zero modes. So this is when the wave function associated with one of these Majorana operators is localized in real space. Okay, so that's what I'll show on the next slide. So the one realization is inside the core of vortices in P-wave superconductors. So, okay, so let's discuss P-wave superconductors. So a superconductor, just really briefly, I'll have to go really quick through what a superconductor is. It's a condensate of electron pairs. These electron pairs are called qubit pairs. And a superconductor has no available low energy states. And one way to think about that is because all the electrons are formed into these pairs, and that means that there's no available states. That changes if you put a vortex in a superconductor. So a superconductor could have a vortex in it. It's a topologically protected excitation. It's essentially a hole in the superconducting condensate. So one way to create these vortices in an electronic superconductor is to apply an electric field. It also happens if you rotate a superfluid or a superconductor, you'll make vortices. Okay, so, and what I claim is that these vortices can host these exotic Majorana particles. So, okay, so here's a classical vortex, not a quantum vortex. We had these in Louisiana.
Quantum meteorology.
That's right. Here's some quantum vortices. So these are rotating BECs from Eric Cornell's group at Gilla. So these are not in a charged superfluid. This is in a neutral Bose-Einstein condensate of rubidium, but these are quantum vortices. So to make a Majorana fermion, you can't just use vortices in a BEC or even vortices in a regular S-wave superconductor. You have to use a funny type of superconductor called a P-wave superconductor. So, however, so vortices can always have low energy states, but they are only Majorana fermions in the case for P-wave superconductors. Okay, and this was first shown in 2001 in this article. So, okay, so I just want to briefly discuss Majorana zero modes in vortex cores. So here's my cartoon picture of a P-wave superconductor, and I'm not going to prove it, but I'm just going to tell you that there are Majorana states associated with each of these vortices. So that was shown by Ivanov, and also, there's a related article by Reed and Green that I didn't include the reference, but I can get that reference to you if you want. Okay, so just to be clear, the green is just my superconductor, and these are my pictures of vortices. Each vortex has one Majorana. Okay, so what that means is that it can host one Majorana fermion. Okay, the other half of the, so you know, a Majorana is like half of a electron state. The other half is in another vortex. It can be any other vortex. Okay, so if you add, so there's no such thing. So outside of this superconductor, there's no such thing as Majoranas. It's like an emergent excitation existing only in this system. So if you add a real electron, it has to split up and go into two Majoranas. In some sense, it's like saying the electron wave function is sort of split between these any two of these vortices. Okay, and there's many ways to do this. So I've sort of drawn a cartoon here. So I've imagined that there's one electron associated with these two Majorana vortices, one electron associated with these two, etc. So here, you know, if I have 8 vortices, there's, you know, electrons in every possible pair. And you should imagine there's, you know, the quantum aspect of this is that there's many possible ways to do this. Okay, so, you know, roughly speaking, regular electron states are stretched between these two vortex cores. Okay, so how big is the Hilbert space? Well, that's a good question. So if we have 2n vortices, each pair of vortices either has 0 or 2 Majoranas. So either has 0 real electrons or 1 real electron. 1 real electron is 2 Majoranas. And these are degenerate states. They're both at 0 energy. And so we have a 2 to the n dimensional Hilbert space. Okay, so that's analogous to having n qubits, if you want to think about it like that. And if we want to implement a quantum operation, so you're supposed to imagine that the way these, if they could braid these, which they can't, as we've discussed, but if they could, they would pair the system with, by putting electrons in certain pairs of vortices, and then they can braid the vortices, and then they can try to measure them, do a measurement at the end. Okay, so this braiding is a non-abelian process, and I'll discuss the braiding in more detail in a subsequent slide. And the way you would read it out is that you bring pairs of vortices together. So if I have a pair of vortices that's far apart, so basically they're only truly Majorana states when the vortices are far apart. If you bring them together, the Majorana states on these two vortices essentially hybridize, and that they're no longer degenerate, and you can measure the difference between having 0 or 1 states on that pair of Majoranas, and you can measure that. So basically, if I bring a pair of vortices close together, I can detect whether that pair of vortices has an electron associated with it or not. Okay? Is there a question?
How are they, I mean, I guess maybe this is where the topological superconductor comes in. These are vortices, they're not interacting. This isn't a Kosterlitz-Alice phase. This is a Rose-Glass.
No, it's not a Kosterlitz-Alice phase. We're just imagining we somehow prepare vortices and we're able to control their location in space. And that's what makes it experimentally impossible.
Yeah, sorry.
Is that they, what's that?
I just apologize.
Oh, that's no problem. Yeah. So you're supposed to imagine that essentially if I combine any pair of these vortices, then I can measure whether or not there is 0 or 1 fermion in there. And that's sort of a quantum measurement, meaning that I could get, you know, I'll get 0 or 1, but well, I'll discuss that in a little bit more detail. But essentially, what I want to say is that you can measure this, we're claiming that you can measure this level occupation and therefore measure the state of the system after braiding them. Okay, so I wanted to discuss next how this braiding would work in principle. So, so the braiding operation, so we want to define a braiding operator to act on our Hilbert space, this Majorana Hilbert space, and it must obey the rules of the braid group. So, so imagine I define a quantum operator, T hat, that braids vortices I and I plus 1. So here are these are 4 vortices, and they may or may not have a Majorana state in them, and I want to think about braiding these states. So how would I braid them? Well, so what I could do is, and here's time. So what I can do is I can take this blue one, move it here, and move this red one here, so I can braid on the left. And then I can subsequently braid the vortices that started at positions 3 and 4. Okay, so I can have this braid operation. I braided these first, and then I braided these first. So it should be obvious that if I do the braiding in the opposite the opposite order, I'll get the same thing. So here I'm going to do the opposite order. See, here I start with 4 vortices. Now I'm going to braid 3 and 4 first, and then I'm going to braid 1 and 2. And what I'm trying to show here is that because I braided vortices that were separate from each other, there weren't any vortices in common. Essentially, these are equal. These operations are the same. That means if I can define a braid rule, T1, so that it goes from right to left, so T1, T3, that's here, so I braid these two, then I braid these two, is the same as T3, T1. And that shows that these operations commute when braids involve separate vortices. Okay? So
this
yeah.
is the point where I go, how do I see the non-abelianness from staring at this?
it's coming, exactly.
All right.
So this is abelian, exactly. So this
That's
is
what I'm
abelian.
doing.
Yeah, exactly. So this part is abelian.
And so this cannot be used to make a quantum computer.
Well, I have to braid adjacent. I have to do more braiding.
I thought abelian was out.
No, abelian things don't make quantum computers.
They don't, but this is only one type of braiding.
Yeah.
So basically,
What
I
else you get to the next slide?
have to go to the next slide.
I'm just,
Yeah,
I got
we're
a
not there
pizza
yet.
and a beer riding on this. Yeah, I need to know. All right. I mean, I might not be around in 10 years.
No, that's you'll be around. We're gonna let's do more braiding. What about operations that share a vortex? They could be non-abelian. So now I'm gonna have 3 vortices, and I'm gonna first braid on the left, then I'm gonna braid on the right. So here's time. So first I braid vortices 1 and 2. Then I braid vortices 2 and 3. So now I've braid these, and now I braid again the vortices that started at positions 1 and 2. Right. So just to be clear, 1, 2, and 3 don't move. So a braiding operation, between 1 and 2 always braids the first. Okay. So this is a braiding operation. 1, 2, 2, 3, 1, 2. Now what we can do is we can do another braiding operation that gets the same answer. Okay, so if we instead braid vortices at 2 and 3, then we braid at 1 and 2, then we braid at 2 and 3, we end up at the same state. So this state is the same as this. So these are equal. These two possible sequences of braidings are equal, but they it's non-commutative because you can see that this rule, this braid rule, wouldn't be satisfied if I was able to, if these operators commute. So basically this shows a non-commutative nature of braiding operations that share a vortex. Okay, so this is the second braid rule. So these 2 braid rules are sufficient to obtain this operator in the case of Majorana fermions. So this is the part that's non-commutative, this type of braiding operation. So we've derived 2 braid rules, and if I generalize them to n vortices, because of course we want to do this for the case of many vortices, right? So we have 2 rules. One is that they commute if they're not nearest neighbors. That was that case. And if they are nearest neighbors, if there's vortices that, if we do braiding operations that involve the same vortex, then we have this braid rule. Okay? And so now the question is, how can we define an operator for braiding Majoranas that obeys this algebra, right? So we have to define an operator T that involves those gammas that I defined that obeys these 2 rules, right? And remember that what we know about the Majoranas is that they obey this. What Ivanov showed is that a representation for that is given by this operator. So this says that this describes the effect of a braid operation on pairs of vortices. So let's see how this can work on a sequence of Majorana 0 points. So so far we haven't defined whether these Majorana states are occupied or unoccupied, but we're going to do that next. So let's prepare a system in a simple product state. So meaning I'm going to start out with these 4 Majoranas, and now I'm going to put 1 electron in the first 2 Majoranas. So my initial state is 1, so that just means 1 fermion in Majoranas 1 and 2, and 0 and 3 and 4. So product state. Now I want to, and if I was to read out, I would get, if I was to read out in 1, 2, and 3, 4, I would find, the way I would read out is I would bring 1 and 2 close together, and 3, 4 close together, and then the claim is that I would be able to detect whether or not there is a fermion in this state. So I would measure 1 for this pair and 0 for this pair. So that would be the readout. Okay, but now instead of doing the readout, let's try to braid these. And so the simplest braid that you can do is to braid 2 and 3. So let's braid those. Here's time. So now I bring 3 here and 2 to there. And now my final state essentially has this, remember the blue line is a real electron, but that electron is distributed between these 2 vortices. So now if I define my readout to measure 1 and 2, okay, let me just slow down. So the final state is a braid operation on the initial state. So if I take this initial state and I act on it with the braid operator I defined on the previous slide, I'm skipping all the details, but the answer is that you get a state like this that's intrinsically entangled, right? So this says that if I was to look at the state associated with 1 and 2, it's in a superposition of being that this is occupied and 3 and 4 are unoccupied, and 1 and 2 being unoccupied, and 3, 4 being occupied. Okay, so it's in a superposition. What that means is that if you were to measure, if you were to essentially do a readout by bringing 1 and 2 together, the same readout, you would have an average occupation of 1/2 for 1 and 2, and for 3 and 4. And we see that we were able to create an entangled final state. So this is the rough picture for how braiding would work if it was possible to do this in an experiment. Okay? Unfortunately, as we've discussed, it's really hard to do this. So experiments have not achieved braiding in condensed matter experiments. Part of the problem is it's hard to have a P-wave superconductor. There's very few of them. There's other setups, however. There's other experiments that can achieve Majorana zero modes. They also haven't braided anything. So here's some theoretical setups. This is a good review article by Jason Elisea. So essentially this involves junctions between topological insulators and other materials. I won't go into the details, but basically the Majorana zero modes are essentially at the ends of various, here's a gate, there's a Majorana zero modes at the ends of this gate. They would be localized there. Experiments have observed Majorana zero modes, or claimed that there's evidence of them. So if you take an S-wave superconductor, and you put a wire on top of it, and you have an external magnetic field, they essentially can measure these tiny little peaks in the conductance and see evidence of Majorana states at the ends. So you can't, can anybody see there's like a purple dot right there on the ends? That's supposed to indicate the existence of the Majorana, but the problem in this setup, so there's evidence, oh thanks.
Is it visible there?
I still can't see it.
I'm fine with this.
I can see it.
I trust you.
I can see the platform.
They're there, but how are you going to braid them, right? They're there, but it's too hard to braid these because they're.
We can just kill the ones over the stage and none of the others.
Yeah.
Can you do that?
The spotlights are so
It's all right.
right, you turn
Yeah.
everything else off the spot.
The problem, but this was just a warm up to say. So once again, so even if you could see they can get these Majoranas, but they haven't been able to braid these in experiments. That's still the problem. So this brings us to what are called chiral Majorana fermions. So chiral Majoranas are an itinerant version of the Majorana fermion. So itinerant just means they can move. So it's
I have a peanut gallery question, sorry.
Oh, yeah.
I mean, is the peak unambiguous? I remember there'd be quite a bit of debate about how smoking gun that little peak is, you know what I mean?
Oh, it's very, yeah, there's a lot of debate over whether this could be some other low energy state. There's always the possibility of other low energy states that could.
And none of these papers are by anybody at Microsoft?
There could be co-authors from Microsoft.
The one thing you have is from UMD, not Microsoft.
And because what I heard was that they see evidence, but the people dispute the evidence of that's these peaks.
Yeah, no, there's a lot of debate about whether they're actually Majoranas. But even if they were, you still can't braid them. So that's the further problem. So there's a question of whether they're actually Majorana fermions, and there's been a lot of proposals on how to solidify them. But I mean, sort of the only way you can really be sure is to actually find an experiment that would allow you to braid them and show experimental evidence of that. The claim is, the hope is that chiral Majorana fermions, which are a different type of Majorana, they will be easier to braid. They're itinerant, They are charged, so just like Majorana zero modes, they are charge neutral, low energy electronic state. And the claim is that they would be easier to braid. So essentially they would be intrinsically mobile. They would exist in some kind of conducting channel. So here's a cartoon picture of a type of device that would possibly braid chiral Majoranas. So, and this is proposed by Zhang and collaborators in 2018. So recent experiments have shown evidence of chiral Majoranas, and this is where we got involved in this project. So essentially the experiment was done by Menard and collaborators, involved essentially a superconductor with a bit of cobalt on top of it. The cobalt is magnetic, so this is superconducting lead. And then we have a cobalt island on top of it. And that cobalt island essentially is what causes the Majorana states to form, the claimed Majorana states. And so this is where we got involved. So we're condensed matter physicists. So we were just interested in understanding the results of this experiment. And how we could possibly, so going forward, we want to know how we can possibly use these chiral Majoranas for quantum operations. So what they observed in the experiment is they observed a spatially localized state near the edge of the cobalt island. So essentially what we're showing here is the tunneling conductance is a function of position, and there's a ring here, and this ring is claimed to be associated with the edge of this cobalt island. Okay, so they observed this in scanning tunneling microscopy, and the possible claim is that there's this chiral Majorana fermion going around the edge of this island. So what is this state? So superconductors are typically gapped at low energies, as I briefly mentioned before. Roughly speaking, magnetic fields are detrimental to superconductivity. So roughly speaking, what's happening here is that the magnetic field is sort of suppressing superconductivity near the edge of this and leading to a Majorana state. So it's a bit more complicated than that, and I'll get into the details in a little bit. So I'm not sure how much time I have. Probably
4 minutes.
4 minutes?
Yep.
I started late though also,
That's-
but okay.
that's
That's
10
even
minutes late.
including that. Okay, I better go faster. Okay, so I can finish in 4 minutes. So here's our model Hamiltonian. It has a lot of terms. I guess I won't be able to describe all the terms in all detail, but essentially we're describing a superconductor with spin orbit coupling and a magnetic exchange field. So this is the effect of the magnetic island. And essentially what happens is that in this magnetic field, because of the existence of the island, is spatially variant. And so there's a point in space where the local gap in the spectrum goes to 0. So essentially here I'm showing the gap as a function of various magnetic field values for the case of a homogeneous magnetic field. And so the claim is that due to this spatially varying magnetic exchange, the gap in the spectrum goes to 0 at one point in space. So within our model, we model the spatially varying magnetic field to be linear in space. So here's our spatially varying magnetic field due to this cobalt island. And then essentially there's a topological transition between a large magnetic field region, which is topologically non-trivial, and a small magnetic field region where it's topologically trivial. So what you're supposed to imagine is that this spatially varying magnetic field is what creates these Majorana fermions. And so a top view of this setup would be, I want to emphasize, we're not describing a circular island, we're describing sort of a spatially varying magnetic field that increases in the y direction, as I've shown here. And there would be two parallel propagating chiral Majorana modes in this device. So the effective Hamiltonian for each of these chiral Majoranas looks like this. So it's a bit more complicated than the Majorana zero mode case, but is still described by these real operators chi. I'm going to skip over this slide because I'm running out of time, and I want to describe our results. So we essentially just study a topological superconductor with a spatially varying exchange field. And what we find is additional low energy states. So we were trying to understand this chiral Majorana mode, but what we find are additional low energy modes that go beyond this, are in addition to this chiral Majorana. So the chiral Majorana, so this is the energy versus momentum for the states that we find. So here's the chiral Majorana. It has a linear energy momentum dispersion. And here's all these additional states that are called Volkov-Pankratov states. These states are not quite located at the, this is a picture essentially of the wave function of the Majorana zero mode. It's localized right near this transition between the topologically trivial and non-trivial regimes. These Volkov-Pankratov states are split away in space, away from this Majorana zero mode. One thing that we're interested in is how they would detect these VP states in an experiment, and they could do it via a spin-resolved tunneling. So what you're supposed to notice is that this would be the tunneling density of states as a function of position and energy, and this is showing the splitting as a function of position of these Volkov-Pankratov states. And the point is that if you tunnel only one spin state of electrons, you get a very different picture for the tunneling DOS. So this cross-shaped, so the last thing, one thing I want to mention is that this, I told you that we were motivated by these experiments. These experiments also found additional states, low energy states. So the experiments measured, so I told you the experiments saw evidence of chiral Majoranas. They actually found additional states that were not understood. So this is the data, the experimental data as a function of energy and position, and essentially this X shape here is reminiscent of what we find in our calculations. So we think that what they may be seeing in these experiments are these additional VP states. So future work is we want to understand what are the implications of these additional low energy modes for things like how we would use these chiral Majoranas for some kind of quantum experiment. So to conclude, we've discussed Majorana fermions. Majorana zero modes were the hot thing 10 years ago. In principle, they should work, but it's difficult to braid them. There's a new type of fermion called a chiral Majorana mode, a new type of Majorana mode that could be braided in an interferometer device, meaning just by passing a current through some complex device. Recent evidence have seen evidence of these chiral Majoranas, but they also see additional low energy states, also shown in these pictures. And our theoretical work finds that generically chiral Majoranas are accompanied by additional VP states. These additional states, these may be bad for doing quantum computing. So I guess this says that maybe John Dowling is correct. Maybe these additional VP states are going to make things more difficult for actually doing quantum operations with chiral Majorana modes. And one thing I didn't need to mention is we've studied other properties of these low energy states. And so if you want to see more about these, you can see our paper with David. Thanks.
Yeah, one question. So which, in that tenfold way or whatever, which classification is this that you're studying?
Oh, the topological classification system? That's a good question. In the tenfold way, isn't this, so it's a topological superconductor, so isn't this a D3 class, I think?
Okay. And then, so you guys are actually, you're taking some type binding model and you're doing kernel polynomial or something to find the density of states. How do you find the density of states?
Oh, it's an analytical model, and essentially, yeah. So it's not a type binding model; it's a continuum model.
Okay.
And yeah, so you'd have to look at our paper or talk to David if you wanted to know more about that calculation. But yeah, it's an analytical model.
All right.
But now we're heading into copy time.
So what's the temperature of these experiments? Do you have a temperature in your model?
Okay, the models are zero temperature, and the experiments are not at zero temperature, but they're very cold. So David, do you know what the temperature of the experiments
I'm
is?
remembering 3 millikelvin.
Millikelvin.
Yeah, it's in
Five
the
hundred.
yeah.
Okay, so at millikelvin temperature for superconducting standard IBM or Google qubits, the coherence time is on the order of maybe nanoseconds.
Mm-hmm.
So one of the things is that your gate speed should be several orders of magnitude faster than your coherence time.
Mm-hmm.
But I believe for the order of picoseconds for the gate speeds for standard, how fast can I braid? I need to be able to do lots of braids per coherence time in order
Well-
for this to work, even if it works.
Okay, so that's a really good question. So here, the thing that I didn't discuss is how the braiding would work with the chiral Majorana. So instead of physically moving them, the chiral Majoranas, it would be electron, essentially current. It would be the natural electron flow at the Fermi velocity that would implement the braiding. So the braiding would be conducted through passing current at some complicated device. And so that's what makes this better is that it's easier to braid
You don't
fast.
have to actually move the things, but still.
Yeah, you're not physically moving them through some,
But, you know, if you could
Yeah.
come up with this gate to coherence time ratio,
okay,
I mean, if that sucks, it doesn't matter if I can't braid or not.
exactly, exactly.
I think the
So,
coherent time will be a little bit, few orders of magnitude larger if you temperatures have the order of Kelvin.
And
It's my
well,
guess.
I know that if for the Google machine, it's 1,000 gates per coherence time. And I think that they do about, the gate speed is picoseconds.
Oh, okay, that's,
So that's where I'm getting the nanoseconds from.
so, yeah, we would want these electrons to
Within an
move at
order
the-
of magnitude that's approximately correct. So you need to be able to braid these at picosecond speeds.
Okay, that sounds fast.
I know,
They
that's
move,
what-
they
that's
move,
why I brought it up.
you know, electrons in a wire go, you know, 100th of the speed of light, so that's, you know, yeah, that's fast. But, yeah, we would have to look into that in detail.
Yeah, I mean, that would be an interesting number, because
Yeah,
if that number is bad, then you might as well just give up now and I win.
you get your pizza.
Yeah, I eat my
Yeah.
pizza and go home.